Now that we've covered the acid-base equilibria chapter, let's go ahead and just work a series of examples. More examples in addition to what we've already worked throughout the chapter, just to make sure that you're comfortable with different kinds of ways we can ask the questions. So the first question, hypochlorous acid has a pKa of 7.52. What is the pH of a 0.25 molar solution of HOCl or hypochlorous acid, and what is its percent ionization? First, hypochlorous acid. I could write down what it is. I've got the formula right there, but I'm just going to write down HA. Why HA? Because HA is a lot easier to write, and that way I don't have to really care what the acid is. Again, it doesn't matter what the acid is. They all follow the same process. They all partially dissociate to a certain percent. I don't care how much. I just want to know the pH of the solution. It does tell me the pKa, and I do need Ka to solve this question. So I'm going to undo the pKa to find the Ka. Remember again that lowercase p is just a mathematical operation that means negative log of whatever follows. So in this case, pKa just means the negative log of Ka. To undo that, to find the Ka, I take 10 raised to the negative pKa value. That undoes the log and the negative in front of it. So if I take this to find my Ka value, Ka is equal to 10 raised to the negative 7.52, and this is equal to 3.0 times 10 to the minus 8th. Now I've got my Ka value, I've got the initial concentration of my acid, so I'm going to solve this just like I solve every other acid-base equilibrium problem. I'm going to say my weak acid plus water is going to form an equilibrium, forming my conjugate base and H3O+. Initially, I have a 0.25 molar solution of HA. I know water does not factor into this. I don't have any of my conjugate base present to start because the question doesn't tell me I do. And I say I have approximately no H3O+. Again, why approximately? Because the truth is I know that I actually have 10 to the minus 7th molar H3O+ just from water. But I'm assuming that the concentration that's going to be produced in solution is higher than that, so I can ignore it. Change, always negative on the reactant side, positive on the product side. And at equilibrium, 0.25 minus x, and x. Set up your Ka expression. And I know it seems redundant to write this out, but it is a process that you should be following because when these questions get a little bit harder, you have to make sure you know where everything is at. So please write out your complete Ka expression before substituting in what you know the values are. And as before, we're going to assume that we can ignore this x because our Ka value is quite small, 3.0 times 10 to the minus 8th. It's much smaller than 10 to the minus 5th, so we can ignore it. Go ahead and solve through and solve for x. We find x to be 8.66 times 10 to the minus 5th. Now for sig figs, my Ka only had 2 sig figs because again, the log, a log value itself, your sig figs are the numbers after the decimal place. So it had 2 sig figs, so Ka value had 2 sig figs, so this has 2 sig figs. So I'm going to underline where my sig figs are. I just don't want to round it because I don't want to create round off error. Take the negative log of x. Again, x represents my hydronium concentration. And this gives me 4.06, 2 sig figs. So my pH equals 4.06. I've answered the first half of the question. What is the pH of the solution? The other thing it wants to know, though, is the percent ionization. Percent ionization is the part that dissociated versus the whole. So x, how much dissociated, versus what I started with, times 100%. This is 8.66, but 2 sig figs here, times 10 to the minus 5th, divided by 0.25 times 100, and I find my answer here to be 0.035%. So a very small fraction actually dissociated, causing a pH of 4.06. Now underneath here, I've got other problems hidden. Again, I'm used to doing this on a whiteboard, not on this screen. So let me go ahead and hide so we have some room to work. And I realized I could just recreate the PowerPoint, but you know, you only think about that when you're actually recording the video, not beforehand. So I apologize again, I'm used to doing all of this on a whiteboard, so we don't have to worry about space. The next one we're going to answer, though, is ammonia is a weak base with a Kb value of 1.8 times 10 negative fifth. What is the pH of a 0.25 molar solution of NH3? So NH3, you guys should know, is ammonia. So it's giving me the Kb value anyway, which means it's a very straightforward question. I'm going to use the letter B to represent my ammonia, B for base. I'm given the Kb value, and I'm given the initial concentration. So B plus water is going to form a conjugate acid, Hb plus, and OH minus. It is a base, so hydroxide is being formed in solution. Initially, I have a 0.25 molar solution of ammonia. I don't have any of my conjugate acid present, and I have approximately no hydroxide present. Set up your Kb expression. Again, we need Kb here because we've got your conjugate acid times hydroxide concentration divided by the base. Whenever you see hydroxide in the numerator, you know you need Kb. Kb equals 1.8 times 10 to the negative fifth. This is the same as x squared over 0.25 minus x. We do ignore that small minus x because our Kb value is 10 to the negative fifth. When we solve for x, we get an x value of 0.0021 molar. But x represents the concentration of hydroxide at equilibrium. This means that I can quickly solve for pOH. Again, that lowercase p just means negative log of whatever follows. So I'm going to take the negative log of the hydroxide concentration, because this equals hydroxide concentration. This gives me 2.68. The other key that this should remind you guys that you are not at pH yet is that you should remember that basic pHs are above 7. This is very low, which means this represents my pOH. To find pH, I know pH plus pOH equals 14. So I'm going to take 14 minus my pOH, or 14 minus 2.68, gives me 11.32. So the pH of the solution, 11.32. What is the pH of a 0.1 molar NH4Cl solution? And it gives me the Kb value of NH3. Now, the first thing you need to recognize here is that this is a salt. If I put that into solution, what's it going to do? And I don't feel like erasing everything and covering it up. So I want you guys, I'm going to work around the space I have. If I put NH4Cl in solution, I know by my solubility rules that this is a strong electrolyte. It will completely dissolve and form NH4 plus ions and Cl minus ions. I then think about what will these two things do in solution. NH4 plus is the conjugate acid of a weak base. So when put into water, this is going to form ammonia plus H3O plus. The fact that it forms or produces H3O plus means that this is an acid. It is the conjugate acid of a weak base specifically. So it is going to cause the pH to be acidic. What about Cl minus? If I put Cl minus into water, it's not going to have any reaction at all. Cl minus is the conjugate base of a strong acid, HCl. Cl minus is a very, very stable conjugate base. It has nothing to gain from accepting a proton from water. or stealing a proton, whichever way you want to think about it. So it's going to stay like that forever and nothing's going to happen. So it's just the ammonia that's going to affect the pH of the solution. So let's give myself some room to work here. Because I know ammonia, or ammonium, is going to form ammonia and hydronium ions in solution, I know that that's what I need to set my ice table up on. Again, ammonium is the conjugate acid of a weak base, ammonia. And so it will react in water to reform some ammonia and some hydronium ion. I'm told initially that I have a 0.1 molar solution of ammonia, or ammonium. I don't have any ammonia, and I have approximately no hydronium. Eventually I'll get it. Okay, the other thing is, though, that when I set up the K expression here for this reaction, I see that I've got ammonia times the concentration of H3O plus divided by the concentration of NH4 plus. Because I have H3O plus in the numerator here, I have to have Ka. Because remember, Ka is the percent of acid dissociation. I am dissociating an acid, so I must have Ka here. So I'm only given Kb. I need to convert to find Ka. We know that Ka times Kb is equal to Kw, and we know that Kw is equal to 1 times 10 to the minus 14. So we should be able to quickly calculate our Ka value. And if you calculate this out, I'm going to let you guys do that one yourself, but you should find the Ka value here to be equal to 5.56, two sig figs. I'm going to write 5.56 just so I don't lose precision in my answer, but 5.56 times 10 to the minus 10. So solve for your Ka value, and you're going to find it to be this value. We know this is equal to x squared, 0.10 minus x, and this equals 5.56 times 10 to the minus 10. I'm going to ignore this x, assume it goes to 0. That Ka value is very, very small. Okay, and when I determine the value of x, remember x again equals the concentration of hydronium ion at equilibrium. My concentration of x is equal to 7.48 times 10 to the minus 6 molar, negative log of my hydronium concentration is the negative log of x, and this gives me a value of 5.13, which means that the pH here is equal to 5.13. I want you to ask yourself, does that make sense? Does it make sense that a ammonium chloride solution has a pH of 5.13? Yes, it does, because ammonium is a conjugate acid of a weak base, which means it's causing the pH to be acidic. So erase all of that. Okay. Last question on this slide. What is the pH of a 0.3 molar NaF solution? Gives me the Ka of HF, which is 7.2 times 10 to minus 4. Okay. One trick that you can recognize here is that NH4Cl, I give you NH3. Those are not the same things. I know NH3 is a base. It gives me Kb. It means base. So that's hinting that this is going to be an acidic solution. In this example, NaF, I'm giving you NaF, but I'm giving you a Ka value of HF. That's suggesting this is probably going to behave like a base. And it does. But you still need to be able to describe why. If I put NaF into solution, it immediately dissociates into sodium ions and fluoride ions. Na plus is the conjugate acid of a strong base. It comes from sodium hydroxide. It is incredibly stable. There is no reason why it ever wants to do anything else. It lost its electron. It's got its noble gas configuration, and it's happy as can be. Fluoride, on the other hand, is also very electronegative, and has its electron or noble gas electron configuration, yes. However, it's very small. It doesn't have the charge delocalization that the larger atoms do. Because it's so small, it will accept a proton back. It will act as an acid. Or it will act as a base to produce that acid. So F minus in solution plus water wants to form that acid. It wants to form HF. In order to do that, it needs to take a proton from water, forming hydroxide. So NaF, F minus, conjugate base of a weak acid. I'm not going to set up the whole expression here, but I want you guys to. So you be setting up an ice chart on this example here. You should find that you've given Ka, you need Kb. Your Kb value is 1.3. Sig figs are there. I'm going to carry a 9 here, but you should have 2 sig figs times 10 to the minus 11. It's very, very small, so I can ignore that value of x on the subtraction portion. You're going to solve for x, which x is equal to your hydronium concentration, and you're going to find this to be equal to 2.04 times 10 to the minus 6. That 0 is where the sig figs are. You should find your pOH to be 5.69 and your pH of the solution to be 8.31. And should it make sense that your pH is 8.31? Yes, because this is a conjugate base of a weak acid. Okay, let's work some examples. Actually, I have room on the page. The pH of a 0.200 molar weak acid is found to be 3.50. What is the Ka? Well, how do I find Ka? Ka is equal to my products over my reactants. It's A because I've got H3O plus here. So I just need to find the concentrations of these things at equilibrium. Pretty straightforward, right? I'm told that the pH of the solution is 3.50. That means that I can find the hydronium concentration because I know that pH is equal to the negative log of the hydronium concentration. And this equals 3.50, which means my hydronium concentration is equal to 10 raised to the negative 3.50, which is 3.16 times 10 to the minus 4. I know initially this has a concentration of 0.200. This is approximately 0, and this is 0. I know at equilibrium this is 3.16 times 10 to the minus 4, which means this is also 3.16 times 10 to the minus 4, which means that x is equal to 3.16 times 10 to the minus 4. I'm going to plug those values into my Ka expression. And I get an answer of 5.00 times 10 to the minus 7. What if I asked you for the Kb? I could do that. I could say, what's Kb? Once you find Ka, you know this is equal to Kw over Ka. And you could actually tell me the Kb as well. The Kb for the conjugate base, that is. Arrange in order of increasing acidity from left to right. Well, let's think about what we've got here. We've got KCN, H2S, RBOH, CH3NH3Cl, LiNO3, and HClO4. Okay. First, I want to recognize if I have any strong acids or strong bases. I have 7 strong acids, HCl, HBrHI, HNO3, H2SO4, HClO3, and HClO4. So this is a strong acid. increasing acidity from left to right, which means most basic to most acidic. I don't have any other strong acids. I know HClO4 is the most acidic. How about weak bases? I know how to find those off my table. They're my alkaline hydroxides and my alkaline earth hydroxides. I only have one. It's my strong base. Rubidium hydroxide is a strong base. Okay, so now I've gotten rid of these two. I should decide on everything else. Well, I recognize that KCN is a salt. I recognize that H2S is a weak acid. I recognize that CH3NH3Cl is a salt. And I recognize that LiNO3 is a salt. So, I know the weak acid, but I don't want to label it quite yet because I don't know if I have a salt of a weak base that can contend with that for acidity. So let's look at these. KCN is a salt. It is a salt formed of potassium ions and cyanide ions. Potassium ion comes from KOH, which is a strong base, so KCN has no effect on pH. CN minus comes from HCN, which is a weak acid, which means this is a conjugate base. So this is basic, or pH above 7. H2S I know is acidic. CH3NH3Cl. I recognize the nitrogen in here. And if I'm not completely confident, I can always draw out the structure. If I drew out the structure here, I see that I've got CH3NH3 plus and Cl minus. This is a conjugate acid of a weak base. It's a conjugate acid specifically of methylamine, this weak base. But it is a conjugate acid, which means it will act as an acid in solution. So this will be acidic. And then LiNO3, I recognize that that has Li plus and O3 minus. Li plus comes from lithium hydroxide, strong base, neutral. Nitrate comes from nitric acid, strong acid, neutral. So of the ones that are left, I have a basic, 2 that are going to be acidic, and 1 that's going to be neutral. Well, that means that KCN is going to go here because it's basic, and LiNO3 is going to go here because it's acidic, or it's neutral. Now I just have the 2 that are acidic left. So now I'm trying to determine between this and this. It gives me Ka and Kb values. How does that help me? Well, that's telling me how much it's going to dissociate. But the Kb isn't as helpful as I need, right? I really need Ka because I want to know how much this conjugate acid is going to dissociate. So I'm going to convert this to a Ka value. The Ka value is 2.7 times 10 to the minus 11. Now I'm going to compare my 2 Ka values. The larger the Ka, the more it dissociates. Or ionization. Stronger acid. Now that I have that, I can see that CH3NH3Cl, though acidic, is weaker than H2S. And I've ranked all my compounds. Using the following Ka values indicate the correct order of base strength. So when you're thinking about bases, remember stronger acids have weak conjugate bases. Cl minus is from HCl. It's a strong acid. It's the weakest base. The way these arrows are written, the arrows are saying that the one to this side is strongest and this side is weakest. So I need to, right away, I can cross out B because I know that Cl minus is not the strongest base. I know that, let's see, so that's Cl minus. Well, first of all, now I know the answer is A because I know Cl minus is the weakest base of all these. But if I looked at the others, I know Cn minus, NO2 minus, and F minus come from weak acids. Which means that they are basic. I also know that H2O is amphoteric, meaning it's an acid and a base. And by itself is just neutral. So I know it's not the strongest base. So even if I didn't think about the fact that Cl minus is the weakest and water's next, I know it's not going to be none of these. I know it's going to be A, but if I had to compare the Ka values, if I actually had to do it that way, instead of just recognizing again, I know right now that A is it because I know that Cl minus is my weakest base because it comes from the strong acid. But looking at your Ka values here, this should help too. The Ka value tells me how strong the acid is. It is opposite for base, so this is a measure of acidic strength. If I'm looking for base strength, the smaller number, the stronger the base, which is what I see here. Cn minus, followed by NO2 minus, or cyanide followed by nitrite, followed by fluoride, followed by water, followed by Cl minus, or chloride. Okay. Sodium benzoate is a common food preservative. What is the pH of a 0.25 molar solution of sodium benzoate? Gives me the pKa of benzoic acid to be 4.19. Again, pKa is the negative log of the Ka value. And this equals 4.19, which means if I want Ka, I'm going to take 10 to the negative 4.19. And that will give me 6.46 times 10 to the minus 5. So first, I've got the Ka value. But that's not quite what I need because I recognize it says sodium benzoate. But then it gives me a value for benzoic acid. You need to be able to recognize, even if you don't know what sodium benzoate is, you need to be able to recognize that is a salt. The fact that sodium is written in here suggests to me that this is a salt. The fact that benzoate is similar but does not match the word benzoic acid tells me this is a conjugate base. So what does that mean? I need Kb. The Kb value here is 1.55 times 10 to the minus 10. Go ahead and set up your ice table. So you've got your base. I'm going to say Hb plus for the conjugate base, plus water. Sorry, I'm thinking about conjugate acids of weak bases. This is a conjugate base, so A minus plus water. It's going to give you my weak acid. No charge on that. plus OH minus. I'm starting out with a 0.25 molar solution. And none of my acid and approximately no hydroxide. Reactants are always minus because we're always, the way the reaction's written, we're assuming it's going that direction. Products are always plus. So I set up my Kb, and I know Kb is equal to 1.55 times 10 to the negative 10. This equals HA times OH minus over A minus concentration, or x squared over 0.25 minus x. This equals 1.55 times 10 to the minus 10. Kb value is very small, so I can ignore this minus x here. So 1.55 times 10 to the negative 10 times 0.25 to undo that, and then take the square root to find the value of x. I find the value of x to be equal to 6.22 times 10 to the minus 6th, and this is equal to my hydroxide concentration. Find the pOH of this. .20, which means my pH is 8.79. Which of the following is a basic salt? NaCl. NaCl comes from Na+, or breaks apart into Na+, Cl-. Na+, think about sodium hydroxide, completely neutral. Cl-, conjugate base of HCl, very, very stable. This will be neutral. NH4Cl splits up into NH4 plus and Cl minus. NH4 plus is a conjugate acid of ammonia. Cl minus, conjugate base of HCl, very, very stable. NH4 plus will cause a solution to have a pH change, but it will actually be acidic. And KNO2 splits up into K plus NO2 minus. K plus, potassium ion, comes from KOH, strong base, very stable, neutral solution. NO2 minus, nitrite ion, comes from HNO2, which is a weak acid, which means this is a conjugate base, and this solution will in fact be basic. So A, B, and C are all acidic? No. A, B, and C are all basic? No. Neither A, B, nor C are basic? No. C is the correct answer. In a solution with a hydroxide concentration equal to 9.8 times 10 to the negative 11th, is this solution acidic, basic, or neutral? Well, I want you to think about this. If the hydroxide concentration is 9.8 times 10 to the negative 11th molar, how do you solve this question? I mean, you could say, okay, well, let's take the negative log, 9.8 times 10 to the minus 11. This gives me 10.01, which is my pOH. I could then solve for pH, 14.00 minus pOH, which is 14.00 minus 10.01 equals 3.99, so acidic. But I don't even need to do math. The better way to do this is to think through this problem. We have 9.8 times 10 to the minus 11 molar concentration of hydroxide. Water itself has a hydroxide concentration of 1.00 times 10 to the minus 7. This is actually a lot smaller than that concentration, which means that if you math your way out of this, you're going to get the wrong answer. The amount of hydroxide, if you math your way out of this, you might get the wrong answer, is what I mean to say. I want you to be careful, because some students are going to stop here and they're going to say, oh, 10. Don't do that, please. The concentration of hydronium ion in solution is so low compared to what water would normally be. This would be considered neutral. It's so much lower that the solution has to be acidic. Remember, in a beaker, you've got a beaker of water, just water, you've got an H3O plus concentration equal to a hydroxide concentration, and these are equal to 1.00 times 10 to the minus 7. But they're in an equilibrium here. What I've done here is I've lowered this concentration drastically, which means this concentration had to increase. Therefore, solution is going to be acidic. It will be acidic. Okay. Very last question. What is the hydronium concentration? Oh, I forgot there was one in here. Not very last question. Second to last question. Let me erase that so we have some space. Second to last question. What is the H3O plus concentration of a solution with a pOH of 8.7? Well, remember what pOH is. You can find hydroxide concentration from pOH. Ten raised to the negative 8.7 gives you 1.995. I need one sig fig here, but I don't want to round this right now. 1.995 times 10 to the minus 9th molar. I know that my hydronium concentration times my hydroxide concentration equals Kw, which is 1.00 times 10 to the minus 14. So I'm going to plug that in and solve for hydronium. And I get a hydronium concentration of 5 times 10 to the minus 6 molar. And the last one, what is the hydronium concentration of a solution with a pH of 0.824? I know my H3O plus concentration. 10 to the negative 0.824 equals 0.149. My sig figs are right here. 96. Which is 1.50 times 10 to the minus 1, or 0.150, whichever way you want to say it, molar H3O plus concentration. Make sure that you can fluctuate between these because we need to be able to do this in the very next chapter. I hope these additional practice problems helped.